In this lesson, we're going to look at, as it says, inductors in series and inductors in parallel. And we are going to see a very similar result to what we saw with resistors. And really, this should not be surprising to us. Let's recall that for resistors, so let's get a resistor R1 here. Whoa, let me zoom in here a little bit. A resistor R1 and a resistor R2 in parallel, and resistors resist against the flow of charge, so path of least resistance, right? We have the current coming in, it hits this junction, it will either naturally flow more to R2 or to R1, depending which one has the lower resistance. Well, inductors also resist against the flow of charge because of Faraday's law. So we know for a solenoid, right? Let's get a quick solenoid in here quickly. So we have for a solenoid, when the current begins to flow, let's get my current direction in here. When the current begins to flow such that it is going to flow, let's have it go in a direction like this. So the current's going to come in, it's going to flow down the front of the page, into the back, down the front, into the back. So if this is the current, the B field that is going to appear in the solenoid is going to be a B field to the right, and then induced effects are going to try to shut this B field down. So it's going to try to resist, the induced current is going to try to resist the flow of this charge. Well, that's going to become evident when we look at what happens by combining inductors in series and combining inductors in parallel. We will see a very familiar result. So some things never change. Conservation of charge over here for the parallel case, and conservation of energy over here for the series case never changes. So when devices, whether it's an inductor, resistor, or any device, is connected in series, the sum of the voltage drops across device 1, device 2, device 3 equals the total voltage drop across the connection. Notice for our induced voltage, I've left off the negative, so even though we can think of these as voltage drops, just like with Ohm's law, V equals IR, it was often a voltage drop, but we don't put the negative when just talking about the magnitude of the drop. So I'm really just looking at the magnitude of the induced voltages that are here. Well, if we then kind of sub in the L di dt for each of the terms 1, 2, and 3, we get our result here for L di dt, L di dt, L di dt. We can note that for any device in series, the current must be the same through all three devices. So I1 equals I2 equals I3 equals I. So we can drop the subscript off of the di dt's and they all cancel out. And we are left with our very familiar result that for resistors in series they add, for inductors in series they also add. And if we think about it, that really shouldn't be surprising to us, because look at our last page of notes. We saw that the inductance was directly proportional to the length of the solenoid. So the longer the solenoid, the greater the self-inductance value. Well, when we put inductors, solenoids, in series, essentially what we've done is make one big long inductor. So while you will not need the derivation we just went through, we certainly will need the result that inductors in series add. Well, then let's quickly look at the parallel case. We have conservation of charge. Again, some things never change. The current comes in, it will split. When it gets to the junctions, I1, I2, I3, it will recombine at the bottom and form again. So conservation of charge dictates that I1 plus I2 plus I3 equals I total. We can take the derivative of both sides of that equality. We can then look at our Faraday's law relationship, that the voltage equals L di dt. Do a little algebra, voltage divided by L. So we're going to substitute in each of those terms. So that's how we get these terms, just like we did for the parallel case, the same concept. Now, same color, same voltage. We lose all of the voltage terms because we can drop the subscripts. So we lose this term, this term, this term, this term. And we are left with our familiar result, that for resistors, we saw that the equivalent resistance was 1 on R1 plus 1 on R2 plus 1 on R3 equaled 1 on R equivalent, 1, 2, 3. The same is true for inductors. So we use a little different language for inductors. We say resistors resist, and we say inductors or solenoids impede. So impedance. Same concept, but different word just to distinguish whether the resistance to the flow of charge is coming from a solenoid, an inductor, or is it coming from a resistor. So there we have it. Like I said, they are familiar to us both conceptually and algebraically, mathematically, and we will be utilizing these in the future.